Hello, my name is Dave Tang. I'm the Senior Vice President of Corporate Marketing and Communications here at Western Digital. I'll be your host for today and like to welcome everyone here that's attending this event in person at Western Digital's headquarters here in San Jose, California, as well as a warm welcome to those attending from around the world, around the block on our webcast. So today, we'll be spending the next few hours talking about innovations that will have very exciting news, insights, and information to share with you. And towards that end, I just want to remind everyone that we will be making some forward-looking statements. And towards those forward-looking statements, I would like to refer you to our website and SEC filings with information and declarations regarding forward-looking statements. So real quick, for today's event, we're going to be sharing a lot of information regarding the world we live in, and specifically the data-centric nature of the world we live in, right? Individuals, businesses, organizations are continuing to find ways to use data to better our lives, our communities, and our planet. So we're using data to find new ways to share personal experiences, to make more immediate results, as well as create new business models, to help improve our safety and security, as well as to predict the future and even cure disease. Through this use of data, we find ourselves in a virtuous cycle, a cycle of data and innovation. So we have new applications that are unleashing the capabilities and possibilities of data, and the quest for new possibilities leads us to gather increasing amounts of data. And as we're able to gather increasing amounts of data, we're faced with the need for innovation to be able to access those increasing amounts of data. And then having the ability to access increasing amounts of data leads us to new applications yet again that tap into those new possibilities of data. So this virtuous cycle that we find ourselves in is based on more than just the storage of data. In fact, we need new technologies and architectures to be developed to enable the capture and preservation and access and transformation of data. We need these environments to serve as a comprehensive and purposeful approach to being able to support the diversity of data, the applications, as well as the workflows of that data. So what you'll be hearing in today's presentation are new innovations that Western Digital is providing to achieve these purposeful environments so that we can realize the full potential of data. And what we're going to share with you is from our unique perspective in the marketplace. And it's unique because our insights are based on unmatched breadth and depth of capabilities. Our technology leadership spans the range from magnetic recording to solid-state technologies, and our portfolio spans devices to platforms to complete data center systems, as well as consumer solutions and even consumer cloud services. So it's this comprehensive approach, this comprehensive knowledge that we have that enables us to identify, focus on, develop, and deliver innovations that will create more precise and purpose-built environments so that data can thrive and so that we can advance the value of data here in our world. So for today, we have a number of presentations from a few executives at Western Digital, as well as a very special guest that we have that will be joining us. And that will be followed by an open Q&A session. So without further delay, let's get things started.
We believe in the promise of data, the promise to create a world that's more predictive, more precise, more personal. That's why at Western Digital, we're redefining how the world leverages data. We're leading the charge, developing bigger, faster, more intelligent solutions that transform the possibilities of data into reality. From the world's largest data centers to the smart devices that connect us all, Our solutions are the heart of our connected world. By capturing and delivering ever-growing amounts of data, we learn from the past to create a future that's sustainable for the whole planet. Enabling the transformation of massive amounts of data means we help create the shared experiences that bring us together and help deliver your next binge-worthy show. It takes smart data to make cities smarter and more energy efficient. Smart cars are made safer with fast data. Transportation, more efficient with big data. Data enables our connected homes so you can protect what matters most. The data we store is always available, always accessible, providing groundbreaking solutions that can cure diseases and save lives. Defining how the world keeps and leverages data is at the core of what we do. As a trusted partner and advisor, we stake our reputation on providing innovative data solutions and delivering global-scale expertise. That's why at Western Digital, we're always innovating, always creating environments where data can thrive.
Okay, now I'd like to introduce Western Digital's President and COO, Mike Cordano.
Thank you, Dave. It's my pleasure to be here. This kind of event is actually something that I love to do, right? It's not the normal course of our conversation. I spend a lot of time talking externally around the financial performance and other things of the company, which is not the topic of today. This is really about the company's innovation. When we charted the course of our strategy several years back, we made a determination that we wanted to be an aggressive innovation company, and we wanted to use innovation to drive growth across a range of technologies that support storage-centric view of the world. Dave talked a little bit about that. So today is a really exciting time for me to talk. We're going to spend some time today going deeper on big data and some innovations that we have that we think will continue to, as the title says, fuel that for the next decade. First, we want to talk a little bit about data. So we continue to see the evolving world. The data universe is one that is increasingly complex. We think about historically data as a record, so a static set of data, very simple. And then as you move to the right, the value equation, you see data in the form of communication, data in the form of efficiency. Think about that as autonomous cars making decisions very quickly at the edge. And then data as a currency, and I think the analogy you can think of there is we're building an entire economy around data like we did early in the last century around petroleum, right? So petroleum was a currency that generated a number of derivative industries all surrounding that commodity. So data is a commodity. It is something that increasingly we're finding more opportunities to drive value and enhance humankind through that. The other thing I'll note is the richness of the data. In each of these areas, the complexity and richness of data is rapidly growing or rapidly changing. And the easiest analogy, the one to personalize, is in the area of personal content. So as we originally thought about images, pixelated images, now we've moved to 4K video. And the richness of that data, that applies to really all data categories. The richness of it and our ability to get more out of it is continuing to advance. And the growth of these simultaneous vectors is obviously driving an increasing need for storage. The other thing that we've begun to articulate is there's two distinct categories, and again, we're simplifying a little bit, but it gets the message across. There's a big bucket of big data, and there's unique characteristics of that, including scale. So think about exascale here, right? So the data pools are much larger. As you see on the slide, we're accumulating these, and then we're accessing them to obtain insight and create predictions, and then ultimately outcomes. And then on the fast data side, an easy analogy there is, again, the autonomous car. So you have to make instantaneous decisions based upon sensor data, real time in the field, so on the edge. And all of this is an interaction between the data and algorithms which are continuing to enhance our ability to make decisions. The other thing that's changing, and we see ourselves at the forefront of, is the architectures required to cope with these in-market use cases. So in the past, we had these sort of singular architectures where all the infrastructure was attached to an upstream application, a monolithic sort of environment. And that created a situation where all the data was basically separated. It was not in a position for it to be utilized and aggregated in a way to do the things we are doing today. New architectures, as you see on the right, is you're accumulating data in large data lakes, and then multiple applications will access that data. So you have a lot of access points, you have a lot of transformation, and you're continuously updating that. That is a very different set of requirements. And us as an infrastructure provider and innovator, we have to be at the forefront of enabling these things. And you're going to hear more about that today. I talked earlier, the size of the data sets are very different. It was sort of a terabyte world in the past. We're now talking about exascale and data lakes that are very large. And at scale, you have to have different capabilities and requirements. Insatiable growth. We talked a lot about this. We continue to see growth of data happening. Obviously, in this chart, fast data, big data. You can think about that as flash and HDD, perhaps. And what we see is over time, by 2020, still 70% of the data will reside on HDDs. If you go a little deeper and look into the data center, that's even larger. About 90% is what we would predict. And that's what's a problem that needs to continue to be solved, right? So we have a bigger role, increasing role in the data center of HDD versus flash, particularly as we think about this big data context. So today we're going to spend a little time talking about our innovations and the foundational technology that supports our ability to continue the growth of that HDD penetration curve that I talked about, and continue to enable the big data requirements of the future, which is access, cost, capability, and performance. So as you know, we've been innovating on the Helium platform for a number of generations, recently announced a 14 terabyte. And I think the exciting thing is today we're going to talk about what's going to come next. And of course, I'm not going to announce that. I'm going to leave that to some others. So I think we have a really exciting day today. I can't wait to disclose the technological innovation that we have coming. So I'm going to turn it back over to Dave, and we'll keep the party going. Thank you.
So not to keep you in suspense for too much longer, we do want to get the perspective of the data users. We've talked a lot about the applications and use cases for data, both big data and fast data. So to get that perspective from someone who's a user and needs access to new technologies, architectures, and environments for both big and fast data, I'd like to invite Janet George, Western Digital's Chief Data Officer, Chief Data Scientist, to the stage.
Thank you, everybody. Good morning. So our digital universe is really growing. It's like 10x growth of our digital universe. And this has a very strong correlation to the growth of storage. I'm going to talk about that in my slides next. But I also want to touch a little bit upon some key points that Mike mentioned earlier today. One of the things he talked about is the past, the way where we came from. And where we came from, data was very tightly coupled with applications. In that, the data was already put into a storage device which was pre-constructed for a query. All data was pre-constructed for a query, so it was very constrained. The storage was constrained. Now we are going to a world where data is no longer pre-constructed. Rather, this one data piece or multiple data pieces are used by many applications, a multiplicity of applications. Now that has very strong implications right down to the storage. And it's directly connected to this exponential growth of storage. Because when we put the data in a database or some structured form, we automatically assign a schema to that data. So because it is for query purposes and there's a schema associated with that data. Now, we don't use schema. As we go into this new world, we want evolving schemas. We want query to be done dynamically. What does that mean? That means we are not going to be able to do programming with our data, as Mike alluded to. We're going to be able to search from that data, right? And we're going to do massive amounts of query substitution, dynamic query that is being pulled from the storage behind the scenes. I'm also going to talk a little bit about big data transforming multiple industries and how storage is directly connected to this transformation. So as you saw, in the autonomous industry, we have cars. We have taught these cars to drive on its own through historical data and training of that data. But now the car, in the real life, has to go out there and start learning on its own. This is very powerful. So now we are connecting with fast data. Mike also had a key mention about how big data and fast data is tightly coupled. So big data is related to traditional historical data, data growing at very, very high speeds, that as we are uniting the data and it's coming together, we're getting insights from the data. And fast data is basically all of the new data that is being generated by sensors, Internet of Things, and wearables. And this data is now being connected, and we're able to do query on the fly. Couple of industries that are experiencing this deeply: autonomous industry, we talked about transportation. We're also looking at many different industries. One is the surveillance industry. And in the surveillance industry, what we are seeing is class of problems are emerging. These class of problems are related to predictions, pattern matching, facial recognition. We are making strong correlations between them. So as you think about fast data and you think about big data, there's a nice synergy between the two of them. And fast data is really a new paradigm, a new wave, a shift in the way we process our data. There are many competing architectures. Two of them that are leading right now in the industry is the Lambda architecture and the Kappa architecture. The Lambda architecture is very good. It has huge synergies for us personally because the Lambda architecture takes into account the historical layer, where the data is brought together in large storage and processing. So it's a batch layer which helps the processing. It also has a high latency layer. We call it the speed layer. And so this processed data, historical data, big data, is then moved from the batch layer to the speed layer, and then from the speed layer to the serving layer. Kappa architecture is very new, and this one has been evolving in the industry for streaming of fast data. This is bounded and unbounded new streams of data. Now, as we look at this exponential growth of data, what are we seeing? So business data was structured, again, as Mike made a strong point about that. We are seeing that basically we have this unstructured data, and we also have semi-structured data. And this new growth is occurring with machine data, Internet of Things. Even in the manufacturing industry, we are connecting all of our devices to the internet. And this is an area of fast growth for us. AI has a direct implication to this growth of data, right? We saw tens of billions of dollars being invested by companies in our industry just in 2016. All of these investments were actually absorbed by US-based companies and China-based companies. When data is stored at scale, we are able to train very differently than we were able to train with query data. And I think AI applications are going to present the largest growth area for us in the coming years. So I think the big data revolution is just beginning. As you can see, there is a need for exponential storage, and we are not going to be constrained on what we store in our storage devices. We're going to be storing a lot of data. We're going to be treating data at its raw form, storing the raw data, and learning from that raw data. Thank you.
Thank you, Janet. And now I'd like to welcome to the stage Brendan Collins, Vice President of Product Marketing for HDD here at Western Digital. Brendan?
So good morning. I think the last time we had a significant HDD technology event like this was back in 2012 when we announced Helium as a technology platform. That worked out pretty good for us. So you heard Mike talk about fast data and big data, and you heard Janet talk about big data and the applications and the workloads and the drivers behind it. I'm going to talk a little bit about growth in the data center. So if you look at overall growth in the data center, it's growing about 35% per year. And that's across enterprise SSD, performance enterprise SSD, and high-capacity hard drives. If you look at this curve, the blue area represents capacity enterprise HDD, which, by the way, is the technology of choice for big data. You'll see us growing at about a 40% CAGR. It has been for the last 4 years and will for the next 4 to 5 years. That number, if you look at hyperscale cloud customers only, is more like 50 to 60%, and it's extremely volatile. If you look at the relationship between the blue area on the curve, which is capacity enterprise, and gray, which is flash, you'll see that even 5 years from now, as Mike mentioned, 90% of all the data will still be stored on capacity enterprise hard drives. Now, there's a reason for that, and it has to do with economics. If you look at the cost between capacity enterprise hard drives and flash, there's like a 15x delta between the two, right? And that's why capacity enterprise is obviously suitable for big data. The challenge we have as an industry is how do we supply all this capacity, but more importantly, do it cost efficiently? How do we come down that cost curve? The key to reducing cost in high capacity drives is not reducing the BOM cost, because that actually increases every generation. The real solution is growing capacity through areal density growth, right? So then the question is, how are we doing on areal density? So if you look at this chart, the reality is PMR as a technology, areal density growth is declining. If you look at the green portion of the curve, the products that we announced recently, they have areal density roughly less than a terabit. And PMR begins to limit at about 1.1 terabits per square inch. If you look at yellow, we go to TDMR and SMR. They give you marginal improvements in areal density growth. The next problem we have is we have a writability limit when we get to 1.4 terabits per square inch. In order to get past that, we need something that we call energy assist. Now, when you think of energy assist, right, the technology that comes to mind is HAMR, or heat-assisted magnetic recording. Or, as some people call, the technology that's always 2 to 3 years away. We've been developing HAMR in our lab, along with other technologies. And it has significant challenges. It has challenges related to reliability, cost, and complexity. One of the reasons we're here today is to talk about another energy assist technology called MAMR, or microwave assist magnetic recording. MAMR, similar to helium, is not a new technology. It's been around for 8 or 9 years. But similar to helium, we managed to crack the code. We have developed a breakthrough. With MAMR, we can deliver the same areal density growth that HAMR is predicted, but without the cost, without the complexity, and without the reliability concerns. So the rest of the presentation is going to elaborate on this message. So when we talk about areal density growth, there are 2 dimensions, and some of these might seem kind of obvious. The one on the left has to do with pushing track density. The other vector on the right is pushing bit density, and the combination gives us areal density growth. The reason I'm bringing this up is there are some innovations out there, like mechanical servo innovations, that have only to do with TPI, or track density. Now, if you look at our position in the industry, we have been I would say, the undisputed leader in capacity enterprise for the past 5 years. And there are a few underlying technologies that are the basis for that. Right, the first one on the left is helium. Right, everybody is familiar with helium in the context of lower power and density and footprint, but it's also a huge enabler for capacity growth. right? If you think, remember in air, we had a lot of turbulence inside the drive associated with disk flutter. In helium, everything is very, very stable. And it provides a stable platform for the magnetic head to move over that narrow track. The next one over is microactuation. So as we push tracks closer together, we need very fine positioning control on the actuator arm, right? That gives us higher TPI, which enables higher capacity. If you look at the one on the right, the damascene process. This process is probably less well known, but this is a head fabrication process. And this also enables narrower heads, which enables tighter track densities. The second thing it enables is complex head structures. And it's actually one of the key enablers for MAMR, which is one of the things we're going to be talking about today. So the combination of all of these three together enable both higher capacity and higher reliability. So I'm going to start with helium for a second. So when you introduce a revolutionary new technology like helium, you might ask yourself, what is the best measure of success? Right. Well, the first thing is when you make a major technology platform announcement, first thing is predictable execution. In other words, did you do what you said you'd do? And the second thing is market adoption. So we announced helium in 2012, and at that time we said we'll be shipping a new product 12 months later, and we did. In that first generation, we actually doubled the shipments that we expected. And then we introduced 4 new generations after that, and today we've shipped over 20 million units combined. So now we're going to show you a video clip that shows you how helium works. We're going to take you inside the drive, but it will focus on the innovations that we've built into the drive every generation. So we've added an 8-disc, for example, for higher capacity. We've had an improved PCA connector for sealing for long-term longevity. And we also have mechanical improvements around actuation and motor design. So that was helium. The next enabling technology we're going to talk about is microactuation and the role that that plays. We have probably the best mechanical servo team in the industry. We introduced microactuation first in our data center products about 2 years ago when we launched the 10 terabyte drive. And we didn't make a big deal about that at the time. But that technology provides fine positioning. So if my arm is the actuator arm, it provides very fine positioning control out at the tip of the arm where the head is. That gives you optimal placement. The second purpose of microactuation is having a high servo bandwidth design. So imagine if you can achieve 400,000 tracks per inch. It's very, very tight. And it operates very, very well on the desk. But you now take it and you put it into a system where you have noisy fans and you have a lot of vibration. How do I stay on that narrow track and make sure I don't impact adjacent tracks? High servo bandwidth through microactuation addresses that problem. So we can now meet our vibration specs for the product and not have degraded performance, right? That's what that delivers. Now you're going to see a video clip as to how that works. by the way, you'll see 3 different types of actuators: single, milli, and micro. The one on the right is micro. That's real micro actuation, by the way, where it's out at the end of the arm. So there you see the read-write head with the 1s and 0s underneath. So now we're going to switch gears and talk about damascene, right? We talked about this less well-known process. I remember when I joined the company here in 2008, we were doing product planning and technology planning. And in 2010, we had to make a major technology decision, right? At that time, PMR was beginning to decline in terms of areal density capability. And HAMR was the energy assist technology that should launch 3 or 4 years from now, in 2013. At that time, we knew of what the challenges were with HAMR related to cost, complexity, and reliability. And we had to make a decision. Do we invest in PMR? Do we invest in extending the life of PMR? And we decided to invest in a process that was called damascene, that took 2 or 3 years to perfect the recipe and about $300 million of investment. But in parallel, we also chose to continue in HAMR and in parallel also invest in MAMR. Right? So we have 3 pokers in the fire, multiple investments going on. And we chose not to put all our eggs in one basket and go after HAMR. Looking back, that was a very, very prudent choice. If you look at damascene as a head fabrication process versus dry pull, there are two different methods. We used to use dry pull. It's a legacy type head fabrication process, and it's different to damascene. So if you look at the main pole and how it gets built, one uses a process of depositing material, and then you shape the main pole by using ion milling. Now that process is not very accurate, and the geometry is not good. So conversely, if you go to damascene, now this is more prevalent in the chip industry. Here is the opposite. You define a shape using a mold, and then you fill that by electroplating. That process gives you much better geometry and tolerance control. So if you look at the right-hand side, they talk about the benefits of damascene. The first one is tolerance control. That gives us higher track density and improved yields. This design also has a full wraparound shield around the head, and that allows us to direct the magnetic energy into a single track on the disc, and again, not impact adjacent tracks. But probably more important for today is this technology also enables complex head structures. This is what made MAMR possible. So here's a video clip on damascene. So this picture shows you how with damascene, how we can focus the energy into a single track and control the field. So this tease up gives you a teaser of what the next section is going to be about. It's going to be about energy assist. So I'm going to take a break here for a second. Everything you've heard up to now is history, is the past, right? So if you look at the top left, we talked about those 3 enabling technologies that create a platform. Those 3 enabling technologies have allowed us to launch the products that you see on the bottom left side of the screen. Some people ask us, how can you launch an 8 terabyte drive that quickly? So if you look at our hyperscale customers, they expect us to get through a qualification in 4 to 6 months. After we're qualified, they want to ramp to peak volume within 6 to 9 months. You can't do that unless you get to 80, 90% yield in the factory, right? Well, having this type of design margin allows you to have high yields with fast qualifications and fast volume ramps. But that's history, right? The next challenge is this writability limit that's in front of us. The question here is, how do we address that limit? So we have a special guest here today, and I'm going to introduce you to him. His name is Professor Jimmy Tsu from Carnegie Mellon University. Jimmy is an acknowledged expert in the industry, and he's actually one of the initial inventors of MAMR. Smart guy. Jimmy.
Thank you, Brendan. So today I'm going to spend a few slides and tell you about this microwave-assisted magnetic recording, and short for MAMR, right? For enable you to break through this writability limit. So I call this a viable technology for next generation of HDD. So first, let me tell you a little bit about what is this writability limit. So if you look at the surface of a disk, and that is a 12 nanometer thick of magnetic layer, and all your information are stored in it, right? So, and you can see if you have really big eyes or you have an electron microscope, and you see actually this film, 12 nanometer thick film, is made of grains, and the grains are a few nanometer in size, okay? So these grains, and then you record bits, and then what you see is the red and the gray, and they are ones and zeros, okay? And you record. So as you can see, if you want to scale down this bits area to increase the number of bits you put on this disk, and then that you can see your grain size needs to be scaled along with it, right? And you need to reduce the grain size the same scale as you reduce the bit area. Okay? So on the curve on the right, and tells you if you scale down the grain size, that the ideal area density you can have, well, increases accordingly. And then if you get to 4.5 nanometer grain pitch, 4 nanometer grain size, and you can reach around 6 terabits per square inch, okay? And today you are on the right bottom corner, okay? So today's PMR is trying to go that way, right? But as you go that way, then you encounter a problem. Today your grain size is about 7, 8 nanometer in diameter, and so you store energy in it. And if you want to reduce this to 5, 4 nanometers or 6, 5, 4 nanometers, then the energy stored in each grain is smaller because the volume becomes smaller. So therefore, it becomes not stable. Means your information stored in there will get self-erased over time. So what you have to do is to put more energy in these small grains, the same amount of energy you put in the big grains. So your energy density becomes bigger. What that introduces is a problem that magnetic moment becomes much stiffer, okay? So the recording head, the conventional recording head, no longer will be able to reverse that magnetic moment, so you can't write your data into the disk. That is the writability limit. Today, we can only write to big grains, okay? So this just put this in the disk drive. You can see the recording heads in there. You can see the media in there. And if the grain is small and strong, you can write to it, okay? So this MAMR technology introduced a very simple thing, and that's called a spin torque oscillator. And that's embedded in between the write gaps, okay? And just few tens of nanometer devices with 10 nanometer thick of magnetic multi-layer films. And then what you do is you pump a DC current in it, okay? So you flow a DC current, And that DC current is formed by electron flow, right? And the electron, we know, not only carries charge, but it also carries spin. That is your magnetic moment come from, right? So the electron carries spin. That spin, through a quantum effect, and generate a magnetization rotation in this little stack of magnetic films. Okay? One of the films is called field generating film, and it rotates. It rotates at a microwave frequency. Okay, that's where the microwave term comes from. And then, so therefore, on the media underneath, you generate a rotating magnetic field at a microwave frequency. And when a magnetic grain going through underneath of recording head, and it resonate, the magnetic moment of the magnetic grain resonate with this rotating field. And so you will be able to pump energy in it, reverse the magnetization. You can't reverse without this little spin torque oscillator. And you can see on the left, it shows the writability gain, and it also shows the field gradient become much sharper. So you can write transitions, or you can write bits in much higher linear density. Okay. So that's the key of MAMR. With this technology, you see this enable you to follow this ideal area density growth curve until 4 nanometer grain size. You can still write it with the sufficient energy stored in it, and you can still write it and with ease, right? So on the left here, and you see a micromagnetic simulation of this written data on it. Okay, so another important advantage this technology brings is if you look at the one on the left, and that is the random data pattern written by either MAMR written by PMR, the perpendicular magnetic recording technology that we have, and the HAMR will be similar. And what you see is the track width of this data is data pattern dependent. If you have zeros in between, the track width becomes wider. If a lot of ones, the track width becomes narrower. So, and also the transition curvature of the data is curved, right? All these two factors will give you unnecessary overhead for both track density and linear density. Okay. So on MAMR technology, because you have this spin torque oscillator embedded in the recording, in the head write gap, and so it writes a very narrow track uniformly, independent of data pattern, and also the transitions are straight, right? So, but the thing is, the key of this technology is this little magnetic thin film stack you embedded in the right gap. It's the same process. You can use same process, fabricated it as you fabricate the original recording head. So there's no new fabrication process you have to use. It's the same, similar fabrication process you use, and you just need to embed it in it. And another thing is, it does not heat the media, right? It's a magnetic resonance. It's all magnetic, efficient magnetic energy transfer. So with that, you will be able to, if you develop this technology as the Western Digital is doing, and then as you reduce the grain size, and with this MAMR provided writability, your area density will enable you to reach the area density above 4 terabits per square inch, and with sufficient thermal stability, okay? With sufficient energy stored in each little grains, right? So with that, and MAMR, it is viable technology, as I say. I stress that viability because you use exact same process as you fabricate today's recording head to fabricate this technology, okay? And so therefore, there's very minimal reliability issues that I can see, and there's very great extendability. Thank you.
Thank you, Jimmy. So now I'm going to give you the Reader's Digest version of what Jimmy just said. So at a very simplistic level, we're going to talk about the reliability limit and why we need energy assist, right? We talked about the need to go to smaller grains. When you go to smaller grains, you got to go to smaller, narrower heads, right? When you do that, you end up with a weak field, a weak magnetic field, right? In order to address that field, you got to lower the energy barrier on the media. But when you do that, you cause thermal instability, which is why we have this problem at 1.4 terabits. Now, one of the ways to address that is to raise the energy barrier on the media, but then you need to complement that with an energy assist on the head while you're writing, right? This can apply both to hammer or MAMR, but both of them require energy assist in order to scale. So now we're going to take a look at both of these technologies. We're going to start with hammer. So if you look at hammer, we said that heat from the laser lowers the energy barrier on the media and allows us to write with small magnetic fields. And then when the media cools, the data is harder to erase, and we have magnetic stability. Now, if you look at the media here, what happens during the write is you heat that media up to somewhere between 400 and 700 degrees, depending on how hard you're pushing it. Anybody that's been in the hard drive industry knows the sensitivity to reliability. We have an old rule for even every 10-degree rise in temperature, you can cut your reliability in half. This is like 10x that on the media. So probably the biggest single challenge is how do you deal with the reliability associated with this high a temperature? Now look at MAMR, right? Here's the writer on MAMR. With MAMR, we embed a tiny spin torque oscillator inside the writer, right next to the write pole. And that generates microwave fields. That in turn allows us to write the data on the media with lower magnetic fields. The real important thing is this happens at the same temperature as PMR. So if you have a drive today in the data center, say that's running at 40 degrees C. Inside the drive on the media, it might be running 15 or 20 degrees higher, say at 60 degrees C with PMR. MAMR will run at that same temperature. So there's very, very little reliability risk, if any, relative to what we just saw on hammer. So some people ask us, well, what is the breakthrough? The breakthrough is directly associated with the innovative design of this spin torque oscillator and how that creates a precise electromagnetic field to assist in the writing process. Now, the magic sauce behind this is the design and the fabrication process behind that. The design in terms of selecting the right materials and the composition of those materials. But then the simplicity is we get to embed that spin torque oscillator using the same Damascene process that we've been using for the last 5 years. So this is a beautiful thing. It's very simple, and we get to leverage the investments that we've made. So if you now take a deeper look at reliability. So we've been testing both hammer and MAMR heads in our lab, and we've run thousands of hours worth of testing. So if you look at writer lifetime testing versus the probability of failure. So if you look at the red curve here, you'll see the hammer median time to failure. And remember, this is on a log scale. If you look in blue, that's MAMR heads, right? And these are actual test results. The key message here is that MAMR is 100x better when it comes to writer lifetime. The next question might be, what does that mean for our data center requirements? So with these kind of results, we can meet our 2.5 million hour reliability. We can meet our 550 550 terabyte workload per year at 5 years of warranty without any concerns. When we try to do this with HAMR, I don't know if we can ever get there. So now we're going to look at energy assisted. We're going to look at a video clip that explains this. So this is the larger head, larger, wider head with wider tracks. Now you see us reducing the head size with narrower tracks. We can't write anymore, right? That's because of the weaker write field. The answer obviously is energy assist. So now we're going to look at HAMR. So the heat obviously lowers the energy barrier and allows writes, but comes with reliability concerns as we've talked about. It requires special materials that we're going to talk about in a few minutes, which add a lot of cost. And in contrast, now we're going to look at MAMR. Here's the spin torque oscillator down near the right pole. It creates an electromagnetic field to assist in the writing, leverages the Damascene head process that we talked about, but it uses existing materials that we already have today. And it doesn't heat up the disk. So that's MAMR, a beautiful thing. So let's take a second and look at our IP situation within the industry. Today we have over 13,000 patents for both flash and HDD. 7,000 of those are for HDD only. If you look at our Helium, MAMR, Damascene, all of the technologies we've just talked about, 75 of those are being issued for MAMR, with another 46 pending, and we're continuing to develop more. What's maybe of more interest on this chart is the amount of IP and patents we have associated with HAMR. We're one of the leading suppliers that have that many patents on HAMR. So I think we're in an excellent position to be able to judge and characterize and contrast MAMR as a technology versus HAMR. So I think when you look at it, all of these across all of these various areas, it's a commitment to technology leadership and fundamental research. So let's contrast MAMR and HAMR for a second, because this is what we had to do internally. The first thing is we talked about complexity. So when we go from PMR to MAMR, we continue to use aluminum disks. In contrast, when we go to HAMR, first of all, we have to go to glass disks, which are more expensive, and then we have to go to new materials, right? And there's a lot more invention required. Reliability. MAMR, there's no heat, very, very similar to PMR. When you go to HAMR, it degrades the reliability significantly. Ecosystem readiness. You can take out a PMR drive, you can drop in a MAMR drive, everything plugs and plays. When you go to HAMR, because of all the concerns associated with heating and reliability on the disk, we need wear leveling. And wear leveling needs host optimizations. And for you guys who have been around, anytime you need host optimizations, it generally limits adoption in the market. Manufacturability, right? We have demos working today, which you'll see later. We'll be shipping customer samples next year, and we'll be in production in 2019. And we can do that, I would say, with high confidence. With HAMR, there's a lot of unknowns, right? There's a lot of unknowns relative to cost and reliability, Some people even question the basic viability of HAMR as a technology in this space. Lastly is cost. The cost of MAMR, because of the amount of technology we're leveraging from PMR, they're actually very, very similar. In contrast, when we go to HAMR, because there's so much new invention, the BOM cost goes up significantly. If you look at the cost of the lasers and the laser diode and the preamps, special media, BOM cost adders are significant. So I asked myself, even if we could address the reliability concerns, could you even sell this because of the commercial challenges that we have? So when we contrast both of these technologies, it was a no-brainer for us as to which one we had to go with. So with MAMR, you get all the gain without the pain. So let's talk about the technology timeline. So we said we have demos working today. As I said, next year for our customers, we will have full capacity MAMR-based samples, and we will launch it. Now, when I say we will launch this in 2019, we're very confident. This is not the technology that's 3 years away. We're very confident that we can do it because there's not a lot of new invention. There's a lot of simplicity here, which is a nice thing. So now let's talk about what that enables in terms of capacity growth. So if you look at the bottom left side of your screen, you can see us introducing 6 terabytes, going to 8, going to 10, going to 12. And the capacity increments, every generation are getting smaller, right? Because the areal density is slowing. It's gotten so slow in 2017, we're now having to add a disk and 2 heads just to meet the capacity requirement. But that comes with big cost adders, right? If you extend that forward and we go to 1.1 terabits per square inch, maybe we'll eventually get to 20 terabytes, maybe sometime out in 2025, because this is very gradual. In contrast, when you look at MAMR, we can grow that capacity at roughly a 15% CAGR per year. In this case, I'm just picking 40 terabytes as an example, so you'll have a gauge. So we can ship double the capacity, right, at probably the same cost as PMR. Now remember, even at 40 terabytes, we're still just coming up the terabit per square inch curve. We're still below 3 terabits per square inch. And this technology has the legs to go all the way up to 4.5. So you can imagine the capacity points we can ultimately get to. So if we look at MAMR and talk about what are the attributes and what are the benefits to a data center manager. The first thing is because we have PMR-like cost structures, we can meet market expectations around $1 per terabyte. That's what it's all about when it comes to big data. The second thing is because this is a highly leveraged technology base, we're very confident on our time to market and schedule. We will have faster qualifications and hopefully you get through them first time. We will have very high yields in the factory, and as a result, you'll have high reliability in the field with less latent defects. And our supply base doesn't require a lot of reinvention. Everything is very aligned. The 15% areal density growth, do you remember that blue curve that we saw? We can support that level of exponential growth, right, with this type of technology. Then we have energy assist, but at ambient temperature, or PMR-like temperatures. What that does, that allows us to continue to meet the reliability levels that we have today with full peace of mind and with 5 years of reliability or 5 years of warranty. Longevity, right? Today we're struggling with PMR, we're inching out little increments. This is good for another decade, as I said, up to 4.5 terabits. And lastly, host interoperability. This is plug and play. You can see why I'm in love with this technology. This also begs the question, what does this mean for flash and the relationship between flash and HDD in the data center? right? All of the analysts in the room here will know how difficult it is to forecast out 3 to 5 years, right? We're trying to go all the way out to 2030. So if you start at the top left and start with flash, when we started shipping SSDs in a meaningful way into the market in 2008. At that time, we had SLC in the market, and the price was coming down roughly 60 to 70% per year. A few years later, we introduced MLC, and we dropped down into the 30 to 40% range. And more recently, we're introducing TLC. And as you migrate to 2D to 3D, right, those cost takedowns come down further. We're down in the 20% range here over the next 5 years. And as you go from 22 out to 30, it drops down further to more like 15 to 16%, right? So like any technology, right, the rate of takedowns are slowing. So contrast that to capacity enterprise. On the bottom left side of the chart, you go back to 2008. Remember, at that time, we still had 5-disk Air products, right? That time, dollar per terabyte takedowns were about 30%, right? Then you see the supply constraint there. That was the flood, right? And prices went up a little bit. Right after that, we introduced helium and damascene. But even with those introductions, areal density is challenged, and we're only coming down about 18% per year. And when you get to this year, we're coming down closer to 8 to 10%. Luckily, if you look at the bottom right, we're now back on a 15% dollar per terabyte takedown curve all the way out to 2028. What's significant about this is what you see on the bottom right side of the curve. Is what this enables is at around the same time as flash is slowing down in terms of price takedown, that's when we deliver a 15% boost in capacity or a dollar per terabyte reduction. What that does is that guarantees, because we have a 10x delta between capacity enterprise and disk, that capacity enterprise will be the technology of choice for big data all the way out through this time frame. That probably, to me, that 10x delta is probably as meaningful and as impactful as the technology breakthrough in MAMR itself. So in wrapping up, we said MAMR technology will enable us to get to 40 terabytes and significantly beyond that. But more importantly, MAMR will fuel the next decade of big data. Thank you.
Don't go away. So at this point, we'll open it up for questions, both here in the room as well as online. So why don't we have Brendan, yourself, as well as Mike and Janet come up to the stage. And we'll open it up for questions. And we'll wait for a mic runner to come over so the folks online can hear the questions as well. So, and if you could maybe state your name and your affiliation, your publication, that would be great.
Sure. So I'm Tom Coughlin, and I do a blog for Forbes on storage. And I had some questions. So it sounds like you can continue to use conventional media versus going to iron platinum in implementing the MAMR, which is significant in terms of the development. And it looks like you're saying you can get rid of the track edge curvature, also because your spin torque oscillator is narrower than the track width. Is that right? Okay. And then what do you see? Because this primarily is going to be increasing the linear density, but you're getting a track density increase as well. Going forward, what do you think the ratio of linear density versus track density increase is going to be? What's going to be the breakdown going forward?
Historically, we've been pushing track density more than bit density. When we introduce MAMR, you get a combination of both. So I think, I don't see us really pushing one versus the other, but I mentioned we will be developing TPI technologies to get us up to 1 million tracks, right? That's a combination of next generation micro actuation combined with MAMR technology.
Okay, other questions here in the room? We do have questions coming in from online. We have a question here about our investments and activities in development of both HAMR and MAMR. So given the breakthrough that we've had with MAMR, are we going to continue with investigations or development research work on HAMR?
Yeah, let me take that. So I think we continue to do advanced development around HAMR. We want to continue to learn. We want to be properly deployed to future technology breakthroughs, so we don't want to completely divest or stop activity around HAMR. But as we've stated today, we are committed to MAMR in products. We see that as a primary path for the next decade or so. But as a responsible custodian of technology and the storage industry, we will continue some level of activity around HAMR.
Okay, thanks, Mike. Yes, in the front.
Thanks, Rick Merritt from EE Times. I wonder if you can give me some more color on the trade-offs between hard drives and solid-state drives in the future. What we see is not just in the data center, but in the notebook where the solid-state drive is sort of taken over. So right now the projections have been drives are phasing out at a certain percentage that you probably know better than I do per year in unit volumes while SSDs climb. Will this change that factor at all?
No, I don't think we see that as having a meaningful effect in the client universe. So we, as we made the decision to enter the flash marketplace, we acknowledge that trend. That is a real trend that's happening. Obviously, we're well positioned to take advantage of that through our flash investments. Where we see the real benefit of MAMR, as we described today, is really in big data, in the data center itself, and in our capacity enterprise line. So the client-side activity would continue as we've talked about previously, and as I think you all expect.
Let's see, another question from our online audience. This one actually referring to helium, and the question is regarding helium and the ability to prevent the helium gas from escaping the hard drive. So comments on that?
Well, let me start, Brendan, you add color. So I think what you just described is where the innovation is, right? Everybody knows the sort of molecular benefit of helium in the environment. The innovation and technology development for us was doing two things. One is containing it, which we've demonstrated through multiple generations, and doing that cost effectively. Those are the two dimensions of innovation, and that really is the secret sauce. And you might want to add to that.
You probably saw in the video when we introduced our first helium product and shipped it, and I don't know if we had any leakage-related failures, actually, even in the field. It was that good. But we continue to innovate. So anytime you have a connector, right, that connects into the hard drive, that's a potential leak source. So we came up with a new innovative design, actually in the second and third generations, that improved the sealability even further.
Okay, great. I also have a question on application of MAMR drives, and I suspect this is really in general. Energy assist drives are very high density, high capacity drives. We talked a lot about usage in the data center. Are there applications outside of the data center that these high density, high capacity devices would be ideal for?
So there are adjacent markets that use high capacity drives. The obvious one is video surveillance or the NAS market. And we would generally optimize these data center products for those adjacent markets.
Okay. Janet, do you see, being a data scientist, do you see other
Absolutely. I agree with Jim about data surveillance. This is a huge upcoming area, security, and also we see edge computing coming up. And so we see different storage needs for edge computing.
Okay, great. All right. Another question from the front. Hang on for the microphone, please. Thank you.
Hiromi Sato from Nikkei. So I'd like to ask about the MAMR's shipment. So you mentioned the MAMR's capacity will be 40 terabyte in 2025, but you will start the shipment from 2019. So how much capacity do you prepare for the first time with MAMR?
Yeah. Generally, we do not announce capacities until we get very, very close to the launch date, just as a matter.
I see. Okay.
Okay. And I think there was another question right next to you.
Rick Merritt with the E-Times again. Usually with any engineering innovation, there's always a trade-off. You get something, but you have to give up something. I'm wondering if you can shine a flashlight onto any of the trade-offs, whether it's new componentry that you have to take on here, or interference issues. I don't know. What are the trade-offs?
Let me start, Brendan. So I think we talked about one. The Damascene process is tightly coupled with our ability to do this. Without that, you can't write precisely, or you can't create precisely enough the geometries of the head to actually enable this. So there are enabling platform technologies. So for us, fortunately, we anticipated that need even to extend PMR, but that has been a huge, or is a huge enabler and part of our ability to implement MAMR.
We had this discussion actually with some of our bigger hyperscale customers last week and the week before. And they said, hey, what keeps you guys up at night when it comes to MAMR, right? So, for example, when we launched Helium, the question was, are you guys really sure that this thing won't leak over the life of the product? And when they asked us about MAMR, I had to scratch my head. I couldn't come up with anything. The one thing I could think of is maybe energy assist, right? It does kind of toggle the head, but unlike HAMR, right, where you end up the media, one of the things we're going to have to do is to monitor our test time and qualification processes for writability and make sure that we have sufficient design margin in that area. But everything else, because of the leverage, right, from all the previous technologies, there's very, very little risk, which is what's nice about it.
Interference though? There's a wireless technology going on there. I don't know. The data center manager walks by with his cell phone. There's some frequency.
I'm not a technology expert, but I think when it comes to emissions, these fields are so low, we would not expect any environmental factors whatsoever, any changes or any implications.
Question, what is the microwave frequency you're using versus the actual write frequencies?
I believe it's close to a gigahertz. Maybe we'll clarify that with one of our technologists afterwards.
Yeah, well, we can actually do that. If there's a microphone in the back.
We can tune it from 20 to 40 gigahertz.
Hang on, Tao, we need the microphone. A lot of people online.
So we can tune our microwave assisted recording in the range of frequency from 20 to 40 gigahertz.
You also want to comment on the shielding question?
So, as you know, we have to put in the spin torque oscillator, and that will add more process time in our wafer fab. That's really the only thing that we worry about. The amount of microwave generated is very, very tiny. And because the frequency is so different than other frequency, we don't anticipate there will be any interference at all.
Great. Thank you, Tao.
Thanks.
We
Another
just
question.
found the technology expert
Yeah.
back of the room. Thank you, Tao.
Another question coming in from online. What do we think the power consumption would look like of MAMR versus HAMR?
There's absolutely no difference in power consumption between PMR and MAMR.
And what about HAMR versus PMR? Then?
HAMR, I believe, has a slight increase in power, but not that significant.
Okay. But enough to generate 700 degrees of heat.
Yes,
Yeah.
that
Right.
indeed.
Okay. Let's see, another question that came in regarding head development capability. So the question is, our MAMR technology developed 100% in-house, and do we expect commercial head manufacturers to also be developing MAMR technology?
Yeah, so our MAMR technology is 100% in-house, so both heads and media, the technology to support that is within the four walls of the company.
Okay.
There's another one.
Ian King, Bloomberg News. I know you don't want to pre-announce specific products and. Yeah, I know you don't want to pre-announce specific products and launch dates and things like that, but can you talk about the speed that you expect to introduce this in more general terms, perhaps when we'll see a crossover, anything like that, please?
A crossover between?
Your current technology,
Yeah.
MAMR.
Yeah, so I think the way to think about this, at the highest capacity point, which we just announced a 12 and a 14, The next generation product beyond that will be MAMR and all subsequent generations after that. So that is the crossover.
That's right.
Hi, Jason Jacobs from TechRel Labs. Since MAMR is patented to WD, how does it compare with other similar technologies being developed by other manufacturers?
In terms of the number of patents, or
Performance, cost?
how did?
So obviously there's a lot of cross-licensing going on in this industry. From our standpoint, patent protection is one thing. It's really the ability to apply it, just like with helium. So we think we have some unique breakthroughs that, yes, of course, we'll file patents on, but it's really the application of those technologies and those patents that separate us. So others that don't have the combination of the knowledge of MAMR, some of the breakthroughs we've discovered, and the combination of enabling technologies, all those things are needed to be integrated together to get the benefit. So others will have to figure out how they might try to compete with us on this.
That's right.
Another question coming in from the webcast. We talked, Mike, both you and Janet talked about both big data and fast data. This technology today obviously applies more to big data. There's a question about what are our thoughts about advancements of underlying technologies for fast data?
Well, I'll start and then I'll let Janet. So as we saw in the chart, obviously fast data we're going to continue in the case of flash to progress that. It's scalable. 3D is scalable. We're in the TLC domain now, 3 bits per cell. You saw in the chart, we anticipate that to go to 4 bits per cell. So that will continue to advance that trajectory. Beyond that, there's a lot of activity on other non-volatile memory types, which we are investing really in all, right? So we've got an activity around ReRAM, we're doing work around phase change memory, and we're doing work around MRAM. All of them are potentially uniquely different areas. And at this point, we're continuing to assess how we prioritize between them. But we certainly see those future memory technologies as adjacent growth areas for us. We're active in terms of our development there, and you'll see more from us in the future.
I will add to what Mike said. In the fast data area of growth, traditionally from the big data area of growth, we look at historical data and historical collection processes of data. Now with fast data, we're looking at new methods of collecting data and brand new ways of learning from that data. So if you traditionally did large-scale applications like AI with traditional data sources or even big data, that's changing. The fast data learning is very much more human-centric, biology-focused, where we are learning like the human brain learns with a continuous stream of learning, not just one big monolithic way of learning, but rather as the bounded streams of data come in and our storage is able to capture that data, we can learn in a continuous fashion, reinforcing that learning for the applications that we are looking at.
Yeah, one other thing I'll add, and Martin Fink has talked about this in some recent conferences. As the scale of data gets large enough, one of the next challenges that we'll be involved with solving is how do you move that data to some place in which you can process it. So our view is, we've talked about this publicly, is you're going to need to invert that model. You're going to need to bring the compute to the data, because movement becomes too complex as well as costly at a certain point.
Absolutely. And I would say that you store that data in your storage, so now compute is coming and pre-processing the different storage data.
If I could add one more thing. One of the things we've noticed over the last few years is that workloads are evolving in the data center, right? So we're moving beyond 4K, 16K, 32K, and as we go to unstructured data, right, we're moving to very large transfer links. As we go to very large transfer links, what we see is that the sustained throughput dominates about 90% of the command time. So access and latency becomes less of a concern, right? That's kind of important even when you're comparing flash and HDD. Flash was really big when we compared performance enterprise drives, where you could deliver 100x the IOPS in a random write environment. When you go to an environment, big drives essentially are going to be mainly sequential. right? So if you can deliver a 10x delta in cost between flash and HDD, and the workload is primarily sequential, you can see it's going to be around for a long time.
And that's related to other questions that have come in regarding I/O capability relative to increasing capacity.
So that's a big challenge today. It's called access density in the data center. So every generation we bump the capacity, the random performance stays the same. So the relationship between the two, or the access density, gradually gets worse over time. Now, that's a challenge today. Some of our bigger hyperscale customers are dealing with that in two ways. Some modify their software stacks so that they modify the stack such that the data that gets presented down to the drive has already been sequentialized. Others throw more flash or faster processors at it. But as I said, as that workload and the transfer length changes over time, that will become less of an issue.
I've got a couple questions related to SMR. I'll combine them into maybe a two-parter. The first part is Western Digital shipping SMR technology in hard drives? And secondly, what are we seeing in terms of adoption of host-managed SMR versus self-managed or device-managed SMR?
Yeah, so we did, if you saw it, we did announce and we did ship our 14 terabyte SMR drive last week. So that is a host-managed SMR product. There are three types out there. There's host-managed, host-aware, and drive-aware. Drive-aware is what we use today inside client HDDs, where everything is seamless. What we found is that our bigger hyperscale customers, they really want to manage the placement of data on the disk. So they want host control, which is why host-managed SMR is the way to go. If you look at adoption across the broader industry, I would say the hyperscale customers that own their own file systems, right, are further along on that path. The OEMs are more probably challenged where they have legacy software and it's more difficult to do. But what we are seeing is that all of the big hyperscale guys are making investments in SMR, host-managed SMR, but at varying degrees.
Yeah, and just to put a point on it, so we are shipping both in the enterprise, as Brendan talked about, the 14 terabyte being an example, but also in clients. So we're shipping the two flavors that Brendan has talked about. Yeah.
Great. A question from John.
Thanks. John Ridding with IDC. You talked a lot about the ability to leverage the existing head manufacturing process for making the MAMR heads. Tell me a little bit about manufacturing future generations of disk media with smaller grain sizes, what challenges you might have with that, and how you overcome some of those challenges.
Okay, we're going to pass the microphone back to the technology experts.
Yeah.
We keep researching in our materials and coercivity of the media. There's a lot of stuff being done on how we get the magnetic field into it through exchange coupling layers. There's a lot of research we are doing in media to get the grain size smaller.
Okay, I think this question was addressed during the presentation, but since it's a follow-up, maybe some additional clarity. It's regarding how easy it is to integrate MAMR devices or HAMR devices into the existing ecosystem.
It's completely seamless. It's like replacing one PMR drive with another one. There are absolutely no dependencies.
That's for MAMR.
For MAMR.
On the HAMR side? What would that
on the HAMR side, as we said, because of the concerns with thermals, we need wear leveling, extensive wear leveling, and that does require host optimizations. So if you're dealing with 5 different hyperscale customers, each one of those will have to customize their file system to be able to manage that.
Okay. Looks like we have one more question from the online and this is regarding expected response from competitors. Do you expect competitors to follow your lead? And if so, how much of a lead time advantage do we think we have?
So obviously, I think we would expect a lot of people to analyze closely what we're doing. I think a few factors to think about. One is damascene, and if you don't have it deployed, it takes time and money to get it deployed, and you have to do the innovations around MAMR. So our view would be we have a multiple year at minimum lead here.
We talked about the fact, you could ask Tao, we spent 2 to 3 years just perfecting the damascene process, and we've spent the last 8 to 9 years developing MAMR. If you contrast that to helium when we first launched it, you'll see one competitor even today hasn't launched it in volume. And it's very, very difficult to actually launch a new technology at full volume, at high yields, at high, to get all the metrics right. Very, very difficult to do.
Okay. Yes, in the second row.
My name is Craig Stice with IHS. Just a point of clarification, kind of going back to the host manage versus device manage concept conversation. With SMR, a host managed system is preferable, as you mentioned. Does MAMR also then allow or require host manage, or is it device managed?
It's neither.
Neither.
MAMR is like PMR, but what you can do is you can take a MAMR drive and you can shingle it if you want to push the capacity further.
Okay.
So for sequential, you could actually get a higher capacity shingled or SMR MAMR drive.
Yeah, so complementary and compatible is the way to think about it.
Okay.
Right.
So does that, does MAMR, I guess, shorten the life of SMR?
No, again, I think it's complementary, right? So for those that have the capability, as Brendan described, we would expect them to take a drive with both MAMR and shingled.
I think as you move out in time over the next 10 years and workloads become more and more sequential, SMR actually is more suited towards that.
Right.
So I think a lot of these guys that will have modified their file systems will take advantage of host-managed SMR, and the bulk of the applications out there 5 to 10 years from now will be SMR based.
Thanks.
Okay, if there aren't any other questions, then we'll end the Q&A session, and as well as end the webcast. I would invite all of the folks here that are on site to go out into the lobby area. We have some product and technology demonstrations there, including a working MAMR drive for you to look at. So thanks again for your attendance here on site as well as on the webcast today. We look forward to seeing you in our next event.
Thank you.